Greetings from SJB Institute of Technology. I am Anita, working as an associate professor in the Department of ECE. Today we are going to discuss about Module 3, which is a strip lines and antenna basics. Majorly it consists of two parts. One is strip lines, another one is basics of antennas. So first we'll discuss about first we'll discuss about in strip lines. Different types of strip lines includes microstrip lines, characteristics of microstrip lines, that is a characteristic impedance and effective dielectric constant of a microstrip line, then followed by the losses associated with the microstrip lines, then parallel strip line, coplanar strip line and shielded strip line. All these will have a same basic structure. So it will be consisting of a dielectric substrate and top layer, bottom layer, that is acting as a conducting layer, conducting media. So coming to strip lines, you have a MMIC technology and MIC technology. So in MMIC technology we'll be we'll be constructing the whole microwave integrated circuit in a single monolithic silicon structure. This is a monolithic microwave integrated circuits which uses in between the microstrip lines and the coplanar strip lines, mainly meant for transmitting the information from one point to another point. It is mainly due to their easier in integration with the circuits. We do prefer these type of strip lines. These will come under the category of transmission line, where majorly we'll have 4 different types of where the transmission of microwave signal from one point to another point in a microwave integrated circuit happens very easily and can be integrated very easily. Majorly we have 4 different types. One is parallel strip line, coplanar strip line, shielded and microstrip line, where you can see the RF and micro MMIC devices, which is using a single monolithic microwave integrated circuit. This is a circuit representing a 75 gigahertz power amplifier, doubler, then power amplifier and doubler circuits integrated in a MMIC. So coming to the first part of microstrip lines. So in a microstrip line, as I have told you, it consists of a conducting strip on one side of the dielectric substrate and a ground plane on the other side of the dielectric substrate, which is mainly used in both microwave and computer technology. So because these lines are easily fabricated by using a PCB technique, they have means they are economic and giving a technical merit. These are commonly used for transmission of power in MICs, that is microwave integrated circuits. This is a geometry one can notice here. This is the dielectric media, dielectric material. We call it as a substrate. On the top side you have a microstrip line and on the bottom side you will have a ground plane. So the dielectric material, effective dielectric constant, which we call it as epsilon r. Effective dielectric constant, relative dielectric constant of the relative dielectric constant of the material as epsilon r. And you can observe here the fields which are traveling from top layer to bottom layer. These are the electric fields, and the circular one which are known as a magnetic fields. And the geometry one can notice here, you have a substrate, on the top layer you have a strip line and on the ground plane on the other side. So it is also known as a open strip line. It supports both quasi TEM mode, and the radiation loss will be more in case of microstrip lines, and the discontinuities, that is at these places, discontinuities. Over a balanced strip line, this has advantage as easier fabrication and better interconnection features. And one can notice here, this is the one where you will give a feed input connecting to your circuit through to the source. And this is a geometry, again schematic diagram. one can notice the dielectric substrate with a dielectric constant as epsilon r and height of that dielectric material as h. On the one side you will have a strip conductor with a width as w and thickness of the strip conductor as t, small t. If I place this in a xyz axis, then the field lines which are passing from top layer to bottom layer, the electric fields and magnetic fields one can notice. This is a magnetic field and these are the electric field. The fields which are traveling in the air, we call it as a fringing fields, which has to be addressed, mainly meant for having a losses. And next topic is finding the characteristic impedance. Here characteristic impedance and the effective dielectric constant of a microstrip line. If you observe, to determine the characteristic impedance, majorly these parameters are important. You need to know about epsilon r and the height of the dielectric material, small t indicating the thickness and w indicating the strip width. This is for rectangular case and this is for circular case. So circular, as you will have a diameter d and the rest of the parameters are almost same. So the Z0 value which is given based on the height and the diameter of the wire, which is this condition has to be satisfied. H must be much greater than d. So Z0 equals to 60 by square root of epsilon r into ln by 4h, ln into 4h by d. Z0 of a microstrip line, which is a function of, one can notice here, it is a function of strip line width, that is h, and the thickness, that is d, and the distance between the line, the line and the ground plane, actually it is h, and the dielectric constant of the material, epsilon r value. D indicating in case of circular wire diameter, h indicating the distance. And as the effective dielectric constant epsilon r e, if I want to calculate, first we need to know about the time delay, propagation time delay that it takes in free space as well as in the material. This is in the case of a free space, which is time taken for the wave to propagate in a free space, which is square root of mu naught into epsilon naught. We can usually represent it as 3.33 nanoseconds per meter, meaning if an electromagnetic wave has to travel in a free space, then it takes about 3.33 nanoseconds to travel a distance of 1 meter. So mu naught epsilon naught indicating permeability and permittivity of free space. You can make use these two values, substitute over here and evaluate, you will get this value. Then you can express either in terms of per meter or in terms of per feet. If it is per feet, make use this to substitute and evaluate. So if it is in the case of instead of free space, if I replace the free space with a non-magnetic medium with a relative permeability as 1 and permittivity as epsilon r, then it should be multiplied with 1.106 into square root of epsilon r. That means epsilon r value to be multiplied. Coming to this epsilon r effective, that is effective dielectric constant of the microstrip line. It is related to the dielectric constant of the board material, what you considered. Then one of the person he discovered an empirical formula by conducting an experiment on different dielectric materials. He found by using different materials as 0.475 into epsilon r plus 0.67. It is a 47% of epsilon r value plus some constant. The same thing can be seen in this diagram. Epsilon r effective is 47% of epsilon r plus 0.67 is a relative dielectric constant and effective dielectric constant. The graph shows the variation between epsilon r and epsilon re. You can make use that formula during the conversion process. So now as it can be, the strip line can be of rectangular type or a circular type. Any one can be made use. Suppose if I know one, the other one can be calculated by conversion. So that can be done by using this, that is transformation of a rectangular conductor into a circular conductor, or a circular conductor into an equivalent rectangular conductor. So suppose if I know D value and T value, that is thickness of the microstrip line and the width of the strip line, then that means rectangular kind, if you know, you can transform that into a circular kind by using this empirical formula. So 0.67 into W multiplied with 0.8 plus T by W. So this is the one, it is an empirical equation which is derived by Springfield after which is used for transformation. The limitation of this is thickness to width ratio, that is T by W ratio. It should be between 0.1 to 0.8. Then you can make use this formula. So after knowing that D value or TH values, you can make use epsilon R effective value which we have derived early in this equation to evaluate Z0. Z0 majorly depends upon H by W ratio. If H is less than 0.8 W, then make use this value Z0 for Z0 evaluation. If W is much larger than height, then that is, we also call it as a wide microstrip antenna, like microstrip line. This is thin or narrow microstrip line. So thin microstrip line, make use this. For a wide microstrip line, make use this formula. These are the formulas which are derived by these two persons. So substituting that epsilon R effective value and D value into the characteristic equation. See, first one we have seen the characteristic equation. So epsilon R value effective value and D value, if you, this is the epsilon R effective value, then D value, if you replace into that equation, which results in this. So which is 87 by square root of epsilon R plus 1.41 ln of this equation, where epsilon R indicating relative dielectric constant, H indicating height, W indicating width, T indicating thickness. So if it is for wide strip antenna, then you can make use Z0 formula as H by W into square root of mu by epsilon. So which is you can also evaluate this as square root of mu by epsilon as mu naught into mu r divided by epsilon naught into epsilon r. So mu naught by epsilon naught, square root of mu naught by epsilon naught is nothing but eta naught, which is nothing but free space impedance, which is 377 ohms or 120 pi. For non-magnetic medium, you can make use this formula. Usually characteristic impedance of microstrip line varies between 50 ohms to 150 ohms. Then we'll look into the different types of losses that occurs in microstrip line. So for a non-magnetic medium or for non-magnetic dielectric substrate, majorly we have two types of losses. So they are dielectric losses and ohmic losses. So dielectric loss, this which is due to the substrate. Ohmic loss, it is in the it can be either due to the strip conductor or due to the ground plane. These two losses together usually we express per unit length as means as they are going to attenuate the signal, we call it as a attenuation factor. The other type of loss which what we have in microstrip line is radiation loss. So majorly we have three losses. One is dielectric loss, another one is a radiation loss, another one is a ohmic loss or skin loss. One by one we will look into. First one, dielectric loss. In a lossy dielectric material, that means the material, substrate material, whatever we have considered, dielectric material, obviously it is not an ideal one. Practical one, if you consider, instead of having a dielectric material, you will have a conductivity also. Conductivity you can't neglect. So as this results in electric and magnetic fields in the dielectric, which will no longer in time phase. So the attenuation constant, dielectric attenuation constant, that is alpha d, it can be expressed as sigma by 2 into square root of mu by epsilon. Sigma indicating the conductivity of the dielectric substrate. As it is a attenuation units are neighbors per meter or centimeter. Now coming to the dielectric constant, which can also be expressed in terms of dielectric loss tangent tan theta as sigma by omega E. Substituting this equation into the above, that means here one can calculate alpha d value, that is dielectric attenuation constant, as omega by 2 into square root of mu E tan theta. As it is as we are using a non-magnetic dielectric media, which will have a upper dielectric above the microstrip ribbon is air, Welch and Pratt derived an equation for attenuation constant as 4.34. These two equations, which are derived by these two persons, expressed in terms of decibels per centimeter. And in that equation, as you have a Q as a factor, we call it as a Quilling factor, dielectric filling factor, which can be evaluated based on epsilon Re and epsilon R. Epsilon Re, again you need to calculate from that formula. So that alpha d can also be expressed per wavelength. This is the expression per centimeter, this is the expression per wavelength. So coming to next one, ohmic losses. As you are using a low loss dielectric material, the predominant source of losses are non-perfect conductors. So conductor element which you are considering on the top and bottom layer of the microstrip line, they will have a losses associated with it, that which we need to address. The current density in the microstrip conductor and the ground conductor, as it is not uniform in the transverse plane, the microstrip conductor contributes the major part of the ohmic loss. Hence the conducting attenuation constant due to ohmic losses of a wide microstrip line, which is given by this formula, representing conducting attenuation constant due to ohmic losses, where RS indicating skin resistance or surface skin resistance, and which can be expressed per square meter, 1 by delta into sigma, where delta can be expressed, which is nothing but skin depth, which is square root of inversely proportional to the frequency of operation, square root of pi by f 1 by pi f mu into sigma, expressed in terms of centimeter. By substituting these two, you can calculate alpha c value. Next, coming to the radiation losses. The radiation loss occurs, or radiation loss majorly depends upon the substrate thickness, dielectric constant, as well as the geometry. Lune, which has results, shows that the radiated power to the total power for an open circuited microstrip line as this. Here we have one factor known as the radiation factor, which can be evaluated based on epsilon Re by using this formula. By considering means the radiation factor decreases, you observe here P radiated to PT, which is inversely proportional to the characteristic impedance Z0. The radiation factor, which decreases with increase in substrate dielectric constant. From this formula, you can observe the radiated power effect, which is due to epsilon R value, inversely proportional, whereas the radiation resistance of an open circuited open circuited microstrip line, which is given by this formula. So the ratio of radiation resistance and the characteristic impedance, which must be equal to the small fraction of the power radiated from a single open circuit discontinuity. The radiation loss usually decreases with the characteristic impedance increase. When Z0 increases, P radiated will decrease, and even for lower dielectric constant substrate, radiation is significant at higher impedance levels. So this is about microstrip line. As we have started with microstrip line, module 3 in strip lines, we have covered microstrip line, characteristic impedance and effective dielectric constant of microstrip line, and the losses associated in strip lines, like dielectric loss and radiation loss and skin loss or ohmic losses. These three losses which we have covered in microstrip line. left out with these 3 topics, which we will see in the next class. Thank you.